Induction is reasoning from the specific to the general. If we believe many instances of a schema, and we know of no counterexamples, then we're often tempted to conclude that the schema is true in general. Suppose we believe that a schema holds for every term in our language. For example, P of A implies Q of A, P of B implies Q of B, and so forth. Then we're entitled to conclude a universally quantified version of our schema. For example, for all x, P of x implies Q of x. Incomplete induction is induction where this set of instances is not complete. From a reasonable collection, we sometimes leap to a universal conclusion even though we have not seen all instances. Consider, for example, the function shown here. F of 1 equals 1, and f of n plus 1 equals f of n plus 2n plus 1. If we look at some values of this function, we notice a certain regularity. The value of f always seems to be the square of its input. From this sample, we're tempted to leap to the conclusion that f of n equals n squared. It's a lucky guess. In this case, that conclusion happens to be true, and we can prove it. Here's another example. This one is due to the mathematician Fermat. He looked at various values of the expression 2 to the 2 to the n plus 1 for various values of n, and noticed that they were all prime. So he concluded, or at least conjectured, that the value of the expression was a prime number. Unfortunately, this was not a lucky guess. His conjecture was ultimately disproved, and in fact it was disproved of the very next number in the sequence. He just didn't have the computing capacity to realize it. For us, this is not so good. In logic, we're concerned with logical entailment. We want to derive only conclusions that are guaranteed to be true when the premises are true. Guesses like these can be useful in suggesting possible conclusions, but they're not themselves proofs. In order to be absolutely sure of universally quantified conclusions, we have to be sure that all instances are true. This is called complete induction. The techniques for complete induction vary with the structure of the language to which it's applied. We begin this lesson with a discussion of domain closure, a rule that applies when the Hebron base of a language is finite. We then move on to linear induction, that is the special case where the ground terms in a language form a linear sequence. After that, we look at tree induction, the special case in which the ground terms of the language form a tree. And finally, we look at structural induction, which applies to all languages.